February 15th, 2013. A 20-meter asteroid streaks through the atmosphere above Chelyabinsk, Russia, exploding with the force of 30 atomic bombs. No detection system saw it coming. The blast wave shattered windows across 6 cities, injuring over 1,500 people and exposing a terrifying blind spot in our planetary defense network. This asteroid approached from the direction of the sun, rendering our most sophisticated telescopes useless. The Chelyabinsk event wasn't an anomaly. It revealed the harsh reality that smaller asteroids pose the greatest immediate threat to Earth precisely because they're the hardest to detect. While we've made remarkable progress with missions like DART and advanced detection systems, dangerous objects still slip through our surveillance network regularly. The question isn't whether another surprise impact will occur, but when. The growing threat we can't see coming. Every week in 2025, astronomers add roughly 60 new, potentially hazardous asteroids to our catalog. These are space rocks large enough and close enough to Earth that they could cause significant damage if they hit us. Yet for every asteroid we discover, our detection systems miss dozens more. The fundamental problem is that we're trying to spot dark objects against the blackness of space, often no bigger than a city block, traveling at speeds that would cross the Atlantic Ocean in 20 minutes. Smaller asteroids represent our most immediate threat precisely because they're the hardest to detect. While massive extinction-level asteroids grab headlines, objects between 50 and 150 meters across pose a far more likely danger to modern civilization. These city killers approach Earth roughly once every few decades. Yet our current detection network identifies less than half of them before they enter our immediate vicinity. The 2024 YR-4 asteroid, initially estimated between 130 and 300 feet across, briefly held a 1% chance of impacting Earth in 2032 when first discovered in December 2024. Its late discovery occurred purely by accident during routine observations of a different region of sky. As of January 2025, we have cataloged 34,127 near-Earth objects, a number that sounds impressive until you realize it represents only about 10% of the estimated population. Computer models suggest approximately 1 million asteroids larger than 40 meters cross Earth's orbital path regularly. The vast majority remain completely unknown to us. Each week brings new discoveries that force astronomers to recalculate impact probabilities and revise threat assessments for objects that may have been silently approaching for months or years. Detection becomes exponentially more challenging as asteroid size decreases. A 1-kilometer asteroid reflects enough sunlight to spot from millions of miles away using ground-based telescopes. A 100-meter asteroid produces a signal roughly 100 times fainter, requiring perfect atmospheric conditions and precise timing to detect. Recent discoveries illustrate this difficulty. In March 2024, asteroid 2024 FX3 was discovered just 14 hours before its closest approach to Earth. The 15-meter object passed within 100,000 miles of our planet, closer than many communication satellites. In September 2024, asteroid 2024 W1 was detected only 8 hours before entering Earth's atmosphere over the Philippines. These last-minute discoveries represent successful detections, not failures, yet they demonstrate how easily dangerous objects can approach undetected. City-killer asteroids pose the greatest immediate threat to human civilization. Objects between 50 and 150 meters across lack the global destructive power of extinction-level impactors, but they carry enough energy to obliterate major metropolitan areas. A 100-meter asteroid traveling at typical impact speeds would release energy equivalent to 80 megatons of TNT, roughly 1,600 times more powerful than the atomic bomb dropped on Hiroshima. The blast would instantly vaporize everything within a 5-mile radius and cause severe structural damage across an area the size of Rhode Island. Current statistical models suggest Earth experiences impact from objects this size roughly once every 1,000 years. though this interval represents an average across geological timescales. Our detection capabilities have improved dramatically since 2020, when we were discovering about 1,000 new near-Earth asteroids annually. Modern automated survey systems now identify over 3,000 per year, processing millions of images nightly through sophisticated pattern recognition algorithms. The Catalina Sky Survey in Arizona operates the most productive detection system, identifying roughly 40% of all newly discovered near-Earth asteroids. Linear arrays of CCD cameras capture successive images of the same sky region. Then computer programs identify objects that move against the background stars. This technique works well for larger asteroids, but struggles with smaller objects that produce weaker signals. Despite these improvements, significant gaps remain in our detection coverage. Ground-based telescopes cannot observe during daylight hours, creating a 12-hour blind period each day. Weather conditions eliminate another 30% of potential observation time at most locations. The combined effect means we monitor Earth's cosmic neighborhood roughly 40% of the time under ideal conditions. More troubling, asteroids approaching from the direction of the Sun remain virtually invisible to ground-based detection systems. The 2013 Chelyabinsk meteor approached from this solar blind zone and caught astronomers completely by surprise. Atmospheric entry dynamics make some small asteroids more dangerous than their size suggests. Objects composed of dense materials like iron or nickel survive atmospheric passage more effectively than loosely bound rubble piles. A 50-meter iron asteroid would likely reach Earth's surface intact, while a 100-meter carbonaceous asteroid might fragment completely in the atmosphere. The 2013 Chelyabinsk object measured only 20 meters across, but created an atmospheric explosion visible from 100 miles away because it was moving unusually fast and entered at a shallow angle. These variables make damage prediction difficult even for detected asteroids. Space weather significantly affects our ability to track incoming objects. Solar flares and coronal mass ejections can disrupt radio communications between telescopes and data processing centers. Increased atmospheric ionization during geomagnetic storms introduces noise into CCD images, making faint asteroids harder to detect. The 11-year solar cycle influences these conditions, with peak solar activity reducing detection efficiency by up to 20%. Major solar storms can temporarily blind space-based detection systems, creating windows of vulnerability that could last several days. Our knowledge of distant cosmic phenomena far exceeds our understanding of potentially dangerous objects in our immediate vicinity. The Hubble Space Telescope has cataloged galaxies billions of light-years away, while the James Webb Space Telescope peers back to the universe's earliest epochs. Yet we cannot definitively state whether a city-destroying asteroid will impact Earth next week, next month, or next year. This paradox reflects the technical challenges of detecting small, dark objects against the cosmic background rather than any lack of scientific capability. Current detection programs focus primarily on asteroids approaching from the outer solar system, where they reflect enough sunlight to register on our instruments. Objects on Earth-crossing orbits that approach from the inner solar system remain largely invisible until they pass between Earth and the Sun. This geometric limitation means we may have only hours or days of warning for some potentially catastrophic impacts. The next major asteroid impact will almost certainly come from an object we have not yet discovered, possibly one that remains undetectable until the final moments before impact. Yet these city killers pale in comparison to the cosmic monsters that have shaped Earth's history. Objects so massive they don't just threaten cities or regions, but entire civilizations and the very fabric of life itself. When extinction came from above, 66 million years ago, a mountain-sized rock hurtled through space at 40,000 miles per hour, its 10-kilometer diameter making it larger than Mount Everest. This massive asteroid had traveled through the void for millions of years, pulled by gravitational forces into a collision course with Earth. As it approached our planet, the asteroid carried enough kinetic energy to match 10 billion atomic bombs. The dinosaurs below had no awareness of the cosmic bullet racing toward them, about to trigger the most catastrophic event in Earth's recorded history. The Chicxulub impactor slammed into the shallow seas off the Yucatan Peninsula with unimaginable force. The asteroid punched through the atmosphere in seconds, its massive bulk barely slowed by the thin air. Upon impact, the entire 10-kilometer object vaporized instantly, along with thousands of cubic kilometers of rock from the impact site. The explosion created a fireball hot enough to melt steel, expanding outward at supersonic speeds. Within minutes, this fireball had grown to cover most of Mexico and the Gulf Coast, incinerating everything in its path. The impact excavated a crater over 180 kilometers wide and 20 kilometers deep in mere seconds. Molten rock and vaporized material shot into the atmosphere at velocities exceeding escape velocity, launching billions of tons of debris into space. Some of this material rained back down within hours, heating the atmosphere to oven-like temperatures across the entire planet. The returning debris created a global firestorm that ignited forests and grasslands on every continent simultaneously. Temperatures rose so dramatically that exposed dinosaurs would have been literally cooked alive under the open sky. Massive tsunamis, some reaching heights of 1,500 meters, surged across the Gulf of Mexico and Atlantic Ocean. These walls of water dwarfed any tsunami in recorded human history, carrying the energy to devastate coastlines thousands of miles from the impact site. The waves penetrated hundreds of miles inland, washing away entire ecosystems and depositing marine sediments far from any ocean. Simultaneously, earthquakes measuring magnitude 10 or higher shook the entire planet, triggering landslides and volcanic eruptions on a global scale. The immediate destruction represented only the beginning of Earth's ordeal. Within days, vast quantities of dust and debris blocked sunlight from reaching the surface, plunging the planet into a nuclear winter that lasted for years. Temperatures dropped by 20 degrees Celsius globally, freezing regions that had enjoyed tropical climates for millions of years. Photosynthesis virtually stopped as plants struggled to survive in the perpetual twilight. The food chain collapsed from the bottom up, starving herbivorous dinosaurs first, then the carnivores that depended on them. The evidence for this cosmic catastrophe lies buried in rock layers worldwide. The KPG boundary layer, a thin strip of sediment marking the transition between the Cretaceous and Paleogene periods, contains the smoking gun that revealed the asteroid's role in the extinction. This layer holds concentrations of iridium 100 times higher than normal background levels. Iridium is extremely rare in Earth's crust, but common in asteroids, providing clear proof that extraterrestrial material rained down on our planet 66 million years ago. The same layer contains shocked quartz crystals, formed only under the extreme pressures generated by asteroid impacts or nuclear explosions. Computer simulations have revealed that the asteroid's angle of impact made the extinction far more devastating than it would have been otherwise. The object struck at approximately 60 degrees, the worst possible angle for generating global destruction. This trajectory maximized the amount of debris launched into the atmosphere, while creating the most efficient delivery system for spreading vaporized rock around the planet. Had the asteroid hit at a steeper angle, much of its energy would have been directed into the ground rather than the atmosphere, potentially allowing more species to survive the subsequent environmental collapse. The Chicxulub impact triggered massive volcanic eruptions that compounded the disaster. The shock waves from the impact traveled through Earth's interior, fracturing rock formations and opening new pathways for magma to reach the surface. The Deccan Traps in India, already experiencing volcanic activity, erupted with renewed intensity following the impact. These eruptions released additional greenhouse gases and toxic compounds into the atmosphere, extending the period of environmental instability for thousands of years after the initial impact. This extinction event fundamentally altered the trajectory of life on Earth. The disappearance of non-avian dinosaurs opened ecological niches that mammals have been unable to exploit for over 100 million years. Small, adaptable mammals survived the extinction by sheltering underground and feeding on seeds, insects, and organic debris. Within 10 million years of the impact, mammals had diversified into forms ranging from tiny shrews to creatures the size of bears. This mammalian radiation eventually led to the evolution of primates, and ultimately to humans. Similar extinction-level asteroids continue to orbit through our solar system today. Statistical analysis suggests that objects capable of causing global mass extinctions impact Earth roughly once every 75 to 100 million years. Since the Chicxulub impact occurred 66 million years ago, we have entered the statistical window when another such impact becomes increasingly likely. Current surveys have identified several asteroids over 1 kilometer in diameter that will make close approaches to Earth within the next century, though none currently pose an immediate threat. Yet extinction-level impacts represent only the most extreme end of the asteroid threat spectrum. Far more frequent are smaller objects that never reach the ground but still possess the power to devastate entire regions through atmospheric explosions alone. The Tunguska mystery and modern implications. On June 30th, 1908, something exploded over the remote forests of Siberia with enough force to flatten 2,000 square kilometers of wilderness. The blast knocked down 80 million trees in a radial pattern extending outward from the epicenter. Yet when scientists finally reached the site 19 years later, they found no crater. This absence of an impact crater initially baffled researchers who expected to find evidence of a massive meteorite strike. The Tunguska event had unleashed energy, equivalent to 1,000 atomic bombs, but the destructive agent had seemingly vanished without a trace. Eyewitness accounts from hundreds of kilometers away described a blinding flash that lit up the morning sky like a second sun. The light was so intense that people could read newspapers by its glow from 60 kilometers away. Within moments, a thunderous roar followed the flash, shattering windows and knocking people off their feet across an area larger than most countries. Seismic stations around the world recorded the shock waves, and atmospheric pressure changes circled the globe twice. The explosion registered on barographs as far away as London, demonstrating the sheer magnitude of energy released over the Siberian wilderness. The remote location of the blast in the Podkamenia-Tunguska River region made immediate investigation impossible. Local indigenous people reported that the explosion killed reindeer and set the forest ablaze, but the area remained virtually inaccessible to outside researchers. Political upheaval in Russia, followed by World War I and the Russian Revolution, delayed any serious scientific expedition. When Soviet scientist Leonid Kulik finally reached the site in 1927, he expected to find a massive crater filled with valuable meteorite fragments. Instead, he discovered thousands of fallen trees arranged in a butterfly pattern radiating outward from a central point, with no crater and no meteorite fragments. The mystery deepened when researchers realized the trees at the very center of the devastation remained standing, though stripped of their branches and bark. This pattern indicated that the destructive force had come from above, not from an impact on the ground. The evidence pointed to an aerial explosion that had occurred approximately 8 kilometers above the Earth's surface. The blast had been powerful enough to knock down trees across an area twice the size of Rhode Island. Yet the lack of ground impact meant no crater formed to mark the event. Scientists now understand that the Tunguska event was caused by an asteroid exploding in the atmosphere rather than striking the ground. The incoming object, traveling at speeds exceeding 50,000 miles per hour, encountered increasing atmospheric resistance as it descended toward Earth. The extreme friction and pressure caused the asteroid to heat up rapidly and ultimately disintegrate in a massive aerial explosion. This atmospheric detonation released all the object's kinetic energy in a single instant, creating a shock wave that propagated downward toward the surface with devastating effect. Research conducted in 2025 has refined estimates of the Tunguska object size to approximately 100 feet in diameter, significantly smaller than earlier calculations suggested. Computer modeling of the explosion dynamics indicates the asteroid was likely composed of loosely bound rocky material that fragmented easily under atmospheric stress. The relatively small size of the object makes the scale of destruction even more remarkable, demonstrating that atmospheric explosions can be far more destructive than ground impacts of similar-sized objects. A 100-foot asteroid exploding at the optimal altitude can cause more widespread damage than a larger asteroid that reaches the surface intact. Atmospheric explosions prove particularly devastating in populated areas because they distribute destructive energy over vast territories. Unlike ground impacts that concentrate damage in a localized crater, aerial detonations create shock waves that travel horizontally across the landscape, affecting much larger areas. The Tunguska explosion generated winds exceeding 500 miles per hour that extended outward for dozens of kilometers from the blast center. These hurricane-force winds would have been lethal to any humans in the area, capable of destroying buildings and infrastructure across entire metropolitan regions. The 2013 Chelyabinsk meteor provided a smaller-scale demonstration of atmospheric explosion dangers in a populated area. This 20-meter object exploded over a Russian industrial city, injuring over 1,000 people and damaging thousands of buildings. The shock wave from the aerial burst shattered windows across the city, sending glass fragments flying at high speed and causing most of the casualties. The Chelyabinsk event released energy equivalent to 30 atomic bombs, yet it was roughly 500 times smaller than the Tunguska explosion. The incident highlighted how even relatively small atmospheric explosions can cause mass casualties and extensive property damage in urban environments. Computer simulations of Tunguska-sized events over modern cities reveal the potential for catastrophic casualties and economic collapse. A 15-megaton aerial explosion over Manhattan would generate shock waves capable of destroying skyscrapers and other high-rise structures across the entire borough. The blast would shatter windows throughout the 5 boroughs, turning millions of glass fragments into deadly projectiles. Urban heat island effects would amplify the thermal radiation, potentially igniting fires across vast areas of the city. Emergency response systems would be overwhelmed by the scale of destruction, making rescue operations nearly impossible. The frequency of atmospheric explosions like Tunguska appears higher than previously calculated based on updated statistical analysis of impact rates. Objects in the 50 to 100 meter size range enter Earth's atmosphere roughly once every 300 to 1,000 years. But most explode over remote ocean or wilderness areas where they cause no human casualties. However, as human population density increases and urban areas expand, the probability of a Tunguska-sized event occurring over a major city continues to rise. The implications for modern civilization are sobering. A Tunguska-type event over a major metropolitan area would cause casualties in the hundreds of thousands and economic damage in the trillions of dollars. The blast would destroy critical infrastructure, including power grids, communication networks, and transportation systems across areas spanning hundreds of square kilometers. Recovery would take decades, and the psychological impact on survivors would persist for generations. Unlike ground impacts that create obvious craters, atmospheric explosions leave no permanent geological record, making them invisible threats that strike without warning and disappear without a trace. Yet, atmospheric explosions represent just one category of asteroid threat. Objects that survive their fiery descent through the atmosphere and actually reach the ground create an entirely different type of devastation, one that leaves permanent scars on the landscape and demonstrates the raw destructive power of cosmic impacts. City killers, the 150-foot threat. The most immediate danger to modern civilization comes from objects measuring between 50 and 150 meters across. City killer asteroids strike Earth far more frequently than their massive extinction-causing cousins, lacking the global destructive power to end all life, but possessing more than enough energy to obliterate entire metropolitan areas and kill millions of people in a single impact event. The most famous example of a city-killer asteroid impact sits in the Arizona desert, where visitors can walk to the rim of Meteor Crater and peer into a perfectly preserved impact site. This massive hole in the ground, nearly a mile wide and 570 feet deep, was created by an asteroid measuring only 150 feet across. The Canyon Diablo asteroid was roughly the size of a 15-story building when it slammed into the desert floor approximately 50,000 years ago. Despite its relatively modest dimensions, this space rock released energy equivalent to 150 atomic bombs when it struck the Earth. The moment of impact transformed the peaceful Arizona landscape into a scene of unimaginable destruction. The asteroid approached at roughly 43,000 miles per hour, carrying kinetic energy accumulated during its journey through space. When it struck the limestone bedrock, the entire 300,000-ton object vaporized instantly, along with millions of tons of surrounding rock. The explosion created temperatures exceeding 4,000 degrees Fahrenheit, hot enough to melt copper and turn solid rock into vapor. The blast hurled 175 million tons of pulverized stone into the air, creating a mushroom cloud that rose miles into the atmosphere. The crater's dimensions reveal the devastating power concentrated in relatively small objects. The impact excavated a bowl-shaped depression 4,000 feet across and pushed up a rim of shattered rock that still towers 150 feet above the surrounding desert. The explosion was so violent that it scattered meteorite fragments across a 10-mile radius, embedding iron and nickel chunks deep into the desert floor. Scientists have calculated that the impact generated pressures exceeding 20 million pounds per square inch, enough to instantly liquefy solid rock and create new mineral formations found nowhere else on Earth. Impact energy scales dramatically with asteroid size and velocity. The relationship follows basic physics principles, where kinetic energy increases with the square of velocity and linearly with mass. This means that doubling an asteroid's speed quadruples its destructive power, while doubling its diameter increases impact energy by a factor of 8. A 100-meter asteroid traveling at 50,000 miles per hour carries roughly 64 times more energy than a 50-meter object moving at 25,000 miles per hour. These scaling relationships explain why relatively small increases in asteroid size or speed produce dramatically more destructive impacts. If an asteroid identical to the Canyon Diablo impactor struck Manhattan today, the consequences would dwarf any natural disaster in recorded history. The 15-megaton explosion would instantly vaporize everything within a 2-mile radius of ground zero, creating a fireball hot enough to melt steel and concrete. The thermal radiation would ignite fires across all 5 boroughs, turning the entire metropolitan area into an inferno. The blast wave would travel outward at supersonic speeds, collapsing skyscrapers and high-rise buildings throughout the city. Seismic shock waves would trigger building failures as far away as Philadelphia and Boston, while debris launched by the explosion would rain down across the entire northeastern United States. Urban environments amplify asteroid destruction through several mechanisms that do not exist in natural settings. The urban heat island effect, which makes cities several degrees warmer than surrounding areas, would intensify the thermal radiation from an asteroid impact. Concentrated building density creates more fuel for fires and more structures to collapse, multiplying casualties beyond what would occur in rural areas. Underground infrastructure, including subway systems, utility tunnels, and basement parking garages, would channel blast waves and create additional collapse hazards. Modern building materials and construction techniques offer little protection against asteroid impacts. Glass facades on contemporary skyscrapers would shatter instantly from the thermal flash, sending millions of razor-sharp fragments flying at lethal speeds. Steel frame construction might survive the initial blast better than concrete buildings, but the intense heat would weaken structural members and cause progressive collapse. Underground facilities would provide some protection from thermal radiation, but would be vulnerable to seismic shock waves and debris penetration. Statistical analysis indicates that city-killer asteroids strike Earth approximately once every 1,000 years on average, though this interval represents a statistical average rather than a predictable schedule. The geological record preserves evidence of several crater-forming impacts within the last 100,000 years, including events that occurred during early human history. The 1908 Tunguska event demonstrated that atmospheric explosions can cause city-scale destruction even without creating permanent craters, suggesting that the actual frequency of destructive events may be higher than crater counts indicate. The current inventory of near-Earth asteroids reveals tens of thousands of objects large enough to cause city-scale destruction. Computer models suggest that roughly 25,000 asteroids between 50 and 150 meters in diameter regularly cross Earth's orbital path. Current detection programs have identified less than 20% of these objects, leaving the vast majority completely unknown to astronomers. Each year brings new discoveries that add several hundred previously unknown city killers to our catalog, but the rate of discovery still lags far behind the estimated population of dangerous objects. The sobering reality is that city-killer asteroids represent a clear and present danger to modern civilization. The next city-killer impact could happen next week, next year, or next century, but statistical analysis suggests it will almost certainly occur within the next few thousand years. When it does, the target will likely be an asteroid we have never detected, approaching from a direction we are not monitoring. This race against cosmic odds has sparked the most intensive sky-scanning effort in human history. The hunt for cosmic bullets. Telescopes around the world now operate in a coordinated network, capturing millions of images each night to catalog every space rock that could threaten our planet. This global detection system processes vast amounts of data continuously, identifying objects that remained invisible to previous generations of astronomers. The Catalina Sky Survey in Arizona leads this worldwide effort, operating multiple telescopes that scan predetermined sections of sky each night. These automated systems capture sequential images of the same celestial regions, then feed the data into sophisticated computer programs designed to spot moving objects. The survey's most productive telescope, a 60-inch reflector on Mount Lemmon, can detect asteroids as small as 10 meters across when they pass within a few million miles of Earth. Since beginning operations in 1998, the Catalina Sky Survey has discovered over 8,000 near-Earth asteroids, making it the most successful detection program in history. The Asteroid Terrestrial Impact Last Alert System, known as ATLAS, represents the next generation of sky monitoring technology. For telescopes located in Hawaii, Chile, and South Africa, automatically scan the entire visible sky multiple times each night, searching for objects that move against the background stars. ATLAS can detect a 20-meter asteroid approaching Earth up to 3 weeks before impact, providing crucial early warning time for emergency response planning. The system processes roughly 100,000 images nightly, identifying approximately 300 new asteroids each month through automated analysis. Astronomers distinguish asteroids from the billions of background stars using a technique called the blink method. This process involves comparing multiple images of the same sky region taken minutes or hours apart. Stars remain fixed in their positions relative to each other, while asteroids appear to jump from one location to another between successive images. Modern detection systems automate this comparison process, using pattern recognition algorithms to identify moving objects without human intervention. The computers can process thousands of image pairs simultaneously, flagging potential asteroid discoveries for human verification. The fundamental challenge of asteroid detection lies in spotting extremely dark objects against the blackness of space. Most asteroids reflect only 3 to 5% of the sunlight that hits them, making them roughly as dark as charcoal. These cosmic rocks become visible only when they pass close enough to Earth that reflected sunlight can reach our telescopes. Objects approaching from the direction of the sun remain virtually invisible to ground-based detection systems, creating a dangerous blind spot in our planetary defense network. The 2013 Chelyabinsk meteor approached from this solar glare zone, catching astronomers completely unprepared. Discovery rates for new near-Earth asteroids have accelerated dramatically in recent years. Throughout 2024, detection programs identified over 3,000 previously unknown objects, bringing the total catalog to more than 34,000 near-Earth asteroids. The Catalina Sky Survey alone discovered 1,854 new asteroids during 2024, while Atlas contributed another 1,200 discoveries. These numbers represent a significant increase from discovery rates in 2020, when fewer than 2,000 new asteroids were found annually. The acceleration reflects improvements in telescope technology, image processing software, and automated detection algorithms. The upcoming INEO Surveyor Space Telescope will revolutionize asteroid detection when it launches in 2027. This infrared observatory will operate from a gravitationally stable point in space, allowing it to scan regions of sky that remain invisible to ground-based telescopes. Infrared sensors can detect the thermal radiation emitted by asteroids, making them visible even when they reflect very little sunlight. The INEO Surveyor will focus specifically on finding asteroids larger than 140 meters in diameter, the size threshold for objects capable of causing regional devastation. Mission planners expect the telescope to discover 90% of these potentially hazardous asteroids within 5 years of beginning operations. International cooperation proves essential for comprehensive sky coverage and effective threat assessment. The International Asteroid Warning Network coordinates data sharing between detection programs worldwide, ensuring that newly discovered objects receive immediate follow-up observations to determine their orbits precisely. The Space Mission Planning Advisory Group coordinates the international response to any asteroid larger than 50 meters across with greater than 1% chance of impacting Earth within the next 50 years. These organizations facilitate communication between space agencies, ensuring that critical information reaches decision-makers quickly during potential impact scenarios. Smaller asteroids present the greatest detection challenge despite posing significant threats to populated areas. Objects between 10 and 50 meters across produce extremely faint signals that current ground-based telescopes can detect only when they pass very close to Earth. These city block-sized rocks could cause extensive damage if they exploded over urban areas, yet they often remain invisible until days or hours before closest approach. The Chelyabinsk meteor measured only 20 meters across, but injured over 1,000 people when it exploded over a Russian industrial city. Artificial intelligence and machine learning technologies are transforming asteroid discovery through automated analysis of massive datasets. Advanced algorithms can identify potential asteroids in telescope images with greater speed and accuracy than human observers, processing millions of data points simultaneously. Machine learning systems trained on existing asteroid databases can recognize the subtle patterns that distinguish moving objects from image artifacts or cosmic ray strikes. The Vera C. Rubin Observatory, scheduled to begin operations in 2025, will use artificial intelligence to analyze the 20 terabytes of data it will generate each night, potentially discovering millions of new asteroids during its first 2 years of operation. Despite these technological advances, the race against time continues to find the remaining 90% of potentially hazardous asteroids before they pose immediate threats. Current estimates suggest that fewer than 10% of dangerous near-Earth objects have been discovered and cataloged. The Vera C. Rubin Observatory expects to identify 90% of potentially hazardous asteroids over 140 meters in diameter, providing a much more complete census of objects that could cause regional or global devastation. Yet finding these cosmic threats represents only half the challenge. Once astronomers identify a dangerous asteroid heading toward Earth, the critical question becomes whether humanity possesses the technology and capability to alter its trajectory before impact. This question moved from theoretical speculation to practical demonstration when scientists decided to test our planetary defense capabilities against a real asteroid target. DART's historic impact and lessons learned. At precisely 7:14 p.m. Eastern Time on September 26, 2022, a 1,260-pound spacecraft traveling at 14,000 miles per hour smashed into the asteroid Dimorphos 7 million miles from Earth. The collision marked the climax of NASA's double asteroid redirection test, humanity's first deliberate attempt to alter the trajectory of a celestial object. The DART spacecraft had spent 10 months journeying through space toward this moment, carrying with it the hopes of planetary defense researchers worldwide. This was not science fiction, but a real test of whether we could push a potentially dangerous asteroid off course using nothing more than the kinetic energy of a speeding spacecraft. The mission represented humanity's boldest experiment in planetary defense technology. For decades, scientists had theorized about using kinetic impactors to deflect threatening asteroids, but no one had ever tested the concept in space. The kinetic impactor technique relies on basic physics principles where a spacecraft transfers its momentum to an asteroid upon collision, theoretically nudging the space rock onto a different orbital path. DART would prove whether this approach could work in practice or whether asteroid deflection remained purely theoretical. The technical challenges facing the DART team seemed almost impossible to overcome. The spacecraft had to hit a target measuring only 160 meters across from a distance of 11 million kilometers away. Dimorphos orbits around its larger parent asteroid Didymos at speeds exceeding 24,000 kilometers per hour, making it a rapidly moving target against the backdrop of space. The spacecraft carried no guidance system capable of real-time communication with Earth due to the vast distances involved. Instead, DART had to navigate autonomously during its final approach, using onboard cameras and computer algorithms to identify and track its target. Ground-based telescopes around the world focused on the Didymos system to capture the moment of impact and measure its effects. The Italian Space Agency's LSAQ, a small satellite deployed from DART just days before impact, positioned itself to photograph the collision and its immediate aftermath. These observation platforms needed to work in perfect coordination to document an event lasting only seconds, but representing years of preparation and engineering effort. The impact exceeded all expectations when DART successfully shortened Dimorphos' orbital period by 32 minutes. Before the collision, the asteroid moonlet completed one orbit around Didymos every 11 hours and 55 minutes. After impact, this period decreased to 11 hours and 23 minutes, representing a change more than 5 times larger than the minimum 73-second shift that mission planners had defined as success. The dramatic alteration demonstrated that kinetic impactors could indeed deflect asteroids effectively, validating a planetary defense technique that had existed only in computer simulations. Analysis conducted in 2025 revealed unexpected details about the impact and its effects on asteroid structure. The collision unleashed a massive barrage of boulders that carried more than 3 times the momentum of the spacecraft itself. Researchers tracked 104 individual boulders ranging from 0.2 to 3.6 meters in radius as they shot away from Dimorphos at speeds up to 52 meters per second. These ejected rocks created forces in unexpected directions, suggesting that the deflection mechanism was more complex than simple momentum transfer between spacecraft and asteroid. The ejected boulders clustered into 2 distinct groups rather than scattering randomly across space. The largest debris cluster contained about 70% of the measured objects and was ejected toward the south at high velocities and shallow angles to the surface. This non-random distribution indicated that something unknown was influencing the ejection process. Scientists believe the boulders likely came from specific sources on Dimorphos, perhaps from larger rocks that were shattered by DART solar panels just before the main spacecraft body hit the surface. The mission proved that kinetic impactors represent a viable planetary defense technique, but only under specific conditions. The success of DART depended on having years of advance warning to plan, build, and launch the deflection mission. The spacecraft required 10 months to travel from Earth to its target, and mission planners needed several years before launch to design the mission and calculate the precise trajectory needed for impact. This timeline means that kinetic impactors work only against asteroids discovered years or decades before they pose a threat to Earth. DART's success has fundamentally influenced the design of future planetary defense missions currently in development. The European Space Agency's Hera mission, launched in 2024, will arrive at the Didymos system in late 2026 to conduct detailed post-impact surveys. Hera will gather high-resolution imagery, structural data, and internal composition measurements to refine our understanding of how kinetic impactors affect different types of asteroids. The mission will also study the long-term effects of the DART impact on Dimorphos's orbit and rotation. The unexpected complexity of the deflection process revealed by boulder ejection analysis has prompted revisions to theoretical models used for planning future missions. Scientists now recognize that asteroid deflection involves more than simple momentum transfer between spacecraft and target. The ejection of material during impact can contribute significantly to the deflection effect, but this contribution depends on factors like asteroid composition, impact angle, and surface conditions that may not be known in advance. The DART mission demonstrated that humanity now possesses the technical capability to deflect potentially dangerous asteroids, but significant limitations remain. The technique requires years of advance warning that our current detection systems cannot guarantee for most threatening objects. The majority of potentially hazardous asteroids remain undiscovered, and many of those we do find are detected only months or years before close approach. Even with this proven deflection technology, our planetary defense capabilities remain fundamentally limited by our ability to spot incoming threats with sufficient advance notice. The blind spots in our defense. These detection gaps create dangerous vulnerabilities that could allow city-destroying objects to strike Earth without warning. The most alarming weakness in our planetary defense systems became apparent on February 15, 2013, when a 65-foot asteroid exploded over the Russian city of Chelyabinsk. This space rock approached from the direction of the sun, making it completely invisible to ground-based telescopes until it entered Earth's atmosphere. The asteroid injured over 1,000 people and damaged thousands of buildings, yet not a single detection system on the planet had spotted it during its approach. The Chelyabinsk event exposed a fundamental flaw in our ability to protect Earth from cosmic threats. The solar glare zone represents the most significant blind spot in our detection capabilities. When asteroids approach from the same direction as the sun, they become lost in the overwhelming brightness of our star. Ground-based telescopes cannot point directly at the sun without risking permanent damage to their sensitive instruments. This creates a cone-shaped region of space roughly 90 degrees wide, where dangerous objects can approach Earth completely undetected. The Chelyabinsk meteor exploited this exact vulnerability, traveling through the solar glare zone for weeks before striking our planet. Current estimates suggest that asteroids approaching from this direction remain invisible until they are only hours away from impact. Technical limitations create additional blind zones that compromise our detection network. Atmospheric interference scatters starlight and reduces the sensitivity of ground-based telescopes, making faint asteroids harder to spot during humid or dusty conditions. Weather patterns eliminate observation time at most telescope locations, with cloud cover preventing sky surveys for roughly 30% of nights throughout the year. The lunar cycle creates another detection challenge, as the full moon brightens the sky enough to wash out faint asteroid signals. During the 3 nights surrounding each full moon, detection efficiency drops by nearly 60% for objects smaller than 100 meters across. Statistics reveal the alarming scope of undetected threats lurking in these blind spots. Computer models estimate that approximately 25,000 asteroids larger than 50 meters regularly cross Earth's orbital path, yet current catalogs contain fewer than 7,000 objects in this size range. The remaining 18,000 asteroids include thousands of city killers that could cause catastrophic damage if they struck populated areas. Many of these undetected objects likely spend portions of their orbits within solar glare zones or other observation-limited regions of space. The discovery rate for new asteroids in these blind spots remains significantly lower than in areas with optimal viewing conditions. The concept of imminent impactors represents a terrifying scenario where asteroids are discovered only days or hours before striking Earth. The Atlas telescope system was specifically designed to provide early warning for these last-minute discoveries, with the capability to spot 20-meter asteroids up to 3 weeks before impact. However, even this advanced detection network struggles with objects approaching from unfavorable directions or during poor observing conditions. In 2024, several asteroids were discovered less than 24 hours before their closest approach to Earth, including some that passed within the orbit of communication satellites. These late discoveries highlight how easily dangerous objects can slip through our detection grid. Earth's rotation creates temporary blind spots that could hide approaching threats for hours at a time. Any single observatory can monitor only the portion of sky visible from its location, leaving vast areas unobserved as the planet turns. The rotation cycle means that dangerous asteroids could remain hidden behind the Earth's horizon for up to 12 hours, during which time they could travel millions of miles closer to our planet. International cooperation helps fill some of these gaps by coordinating observations between telescopes on different continents, but significant coverage holes persist. Remote ocean areas and polar regions receive minimal monitoring, creating opportunities for asteroids to approach undetected. Asteroids with unusual orbits or compositions present additional detection challenges that current systems struggle to address. Objects following highly eccentric paths spend most of their time in the outer solar system, where they remain too faint to detect until they swing close to the sun. These asteroids can accelerate rapidly as they approach the inner solar system, giving detection systems very little time to spot them before they pass Earth. Dark asteroids composed of carbonaceous materials reflect as little as 3% of incident sunlight, making them nearly invisible against the black background of space. Some asteroids tumble chaotically as they orbit, causing their brightness to vary dramatically and making them difficult to track consistently. Solar storms and space weather events can disrupt detection systems at critical moments when every hour of observation time matters. Coronal mass ejections from the Sun can interfere with radio communications between telescopes and data processing centers, delaying the analysis of potential asteroid discoveries. Geomagnetic storms increase atmospheric ionization, introducing noise into CCD camera images that can mask faint asteroid signals. The 11-year solar cycle influences these disruptions, with peak solar activity periods reducing detection efficiency by up to 20%. Major solar events can temporarily blind space-based detection systems, creating windows of vulnerability that could last several days during critical observation periods. The discovery of asteroid 2024 YR4 illustrates how detection gaps can create false alarms and missed threats simultaneously. This object was initially calculated to have a 3.1% chance of impacting Earth in 2032, making it the most significant asteroid threat identified in over 2 decades. However, the asteroid was discovered only after it had already passed closest approach to Earth, highlighting how our detection network can miss dangerous objects even when they pass relatively close to our planet. Subsequent observations revealed that 2024 YR4 poses no immediate threat, but its late discovery demonstrates the ongoing vulnerability of our planetary defense systems. The uncomfortable truth about our planetary defense network is that it resembles a security system with multiple doors standing wide open. We have developed sophisticated technologies for tracking asteroids once they are detected, but fundamental gaps in our detection coverage could allow catastrophic impacts to occur without warning. The Chelyabinsk event provided a small-scale demonstration of what could happen when a dangerous asteroid approaches from our blind spots. A larger object following a similar trajectory could cause mass casualties and economic devastation before we even realized it was approaching Earth. These vulnerabilities have sparked an unprecedented wave of innovation in planetary defense technology as scientists and engineers work to develop systems that could protect our planet from threats we cannot yet see coming. Beyond DART, the future of planetary defense. Multiple ambitious planetary defense projects scheduled for the late 2020s and 2030s will transform our ability to protect Earth from cosmic threats. These next-generation systems go far beyond simple kinetic impactors, incorporating advanced detection networks, multiple deflection techniques, and rapid response capabilities designed to handle any asteroid threat we might encounter. The goal is creating a comprehensive planetary defense system that can detect dangerous objects decades before impact and deploy appropriate countermeasures regardless of asteroid size or composition. The European Space Agency's Heron mission represents the next critical step in understanding asteroid deflection technology. Launching in 2024, this spacecraft will spend 2 years traveling to the Didymos system to conduct detailed post-impact surveys of DART's collision site. Hera will arrive in late 2026 equipped with high-resolution cameras, radar systems, and spectrometers designed to analyze the internal structure of dimorphos and measure the long-term effects of the kinetic impact. The mission will map the crater created by DART's collision and study how the impact altered the asteroid's rotation and surface composition. This data will refine computer models used to predict how different types of asteroids respond to kinetic impacts, improving the accuracy of future deflection missions. Nuclear deflection systems are being developed for the largest asteroids that kinetic impactors cannot handle effectively. These weapons would detonate near massive asteroids rather than on their surfaces, using the intense radiation and plasma from nuclear explosions to vaporize surface material and create thrust in the opposite direction. The concept avoids the risks of fragmenting large asteroids while providing enough energy to deflect objects measuring several kilometers across. However, nuclear deflection faces significant technical and political challenges. International treaties currently ban nuclear weapons in space, requiring new agreements before such systems could be deployed. The standoff detonation distance must be calculated precisely to avoid shattering the asteroid into multiple dangerous fragments. Gravity tractors offer a gentler approach to asteroid deflection that works by slowly pulling space rocks off collision courses using gravitational attraction. A gravity tractor spacecraft would position itself near a threatening asteroid and use its own mass to create a tiny gravitational pull that gradually alters the asteroid's trajectory over months or years. This technique requires no physical contact with the asteroid and avoids any risk of fragmentation, making it ideal for loosely bound rubble pile asteroids that might shatter under kinetic impact. The method demands extremely precise navigation and years of advance warning, but it can deflect asteroids with surgical precision while providing continuous monitoring of the threat. Early warning systems scheduled for deployment in the late 2020s will provide decades of advance notice for incoming threats through space-based detection networks. The ENIO Surveyor Space Telescope, launching in 2027, will operate from a gravitationally stable point in space where it can scan regions of sky invisible to ground-based telescopes. This infrared observatory will detect the thermal radiation emitted by asteroids, making them visible even when they reflect very little sunlight. The telescope will focus on finding objects larger than 140 meters in diameter, providing 90% coverage of potentially hazardous asteroids within 5 years of beginning operations. Additional space-based telescopes planned for the 2030s will extend this coverage to smaller objects and provide redundant monitoring capabilities. Rapid response spacecraft systems are being designed to launch within months of threat detection for asteroids discovered with limited warning time. These pre-built deflection vehicles would remain in storage on Earth, ready for immediate deployment when dangerous objects are identified. The spacecraft would carry standardized kinetic impactor payloads or nuclear deflection systems, depending on the size and composition of the threatening asteroid. Rapid response missions require simplified designs that can be assembled quickly without extensive testing, accepting higher risks to enable faster deployment. The concept assumes that some asteroids will inevitably be discovered too late for conventional deflection missions, making rapid response the only viable option. International cooperation efforts are creating a coordinated global defense network through organizations like the International Asteroid Warning Network and the Space Mission Planning Advisory Group. These entities facilitate information sharing between space agencies and coordinate the development of cooperative mitigation plans for asteroid threats. The network ensures that asteroid discovery data reaches all relevant parties immediately, enabling rapid threat assessment and response planning. International cooperation also addresses the legal and political challenges of deploying deflection systems, particularly nuclear weapons, in space. Future planetary defense will require unprecedented levels of international coordination to succeed. The challenges of deflecting asteroids discovered with only weeks or months of warning represent the most difficult scenario for planetary defense systems. Limited time frames restrict deflection options and increase uncertainties associated with any intervention. Nuclear standoff detonations become the primary option for large asteroids detected at short notice, despite the risks of fragmentation. Smaller asteroids might be deflected using kinetic impactors if rapid response spacecraft can reach them quickly enough. However, asteroids discovered very close to impact may be impossible to deflect, requiring emergency evacuation of threatened areas instead of deflection attempts. Advances in propulsion technology will enable more effective deflection missions through faster transit times and greater maneuverability. Ion propulsion systems can accelerate spacecraft to higher velocities over extended periods, reducing travel time to distant asteroids. Solar sails harness radiation pressure from sunlight to provide continuous thrust without requiring propellant, enabling long-duration missions to slowly push asteroids off course. Nuclear thermal propulsion could cut travel times to months instead of years, making deflection possible for asteroids discovered with minimal warning. The vision for comprehensive planetary defense encompasses a multi-layered system capable of protecting Earth from cosmic impacts of any size through robust detection networks, multiple deflection technologies, and international cooperation. Space-based telescopes will provide decades of advance warning for most threatening asteroids, while rapid response systems handle late discoveries. Kinetic impactors will deflect smaller asteroids, nuclear systems will handle the largest objects, and gravity tractors will provide precise deflection for sensitive situations. This integrated approach ensures that humanity will never again face the prospect of surprise asteroid impacts capable of causing regional or global devastation. Yet, building this comprehensive defense network requires massive financial investment, raising fundamental questions about the true cost of protecting our civilization from cosmic threats, the economics of cosmic catastrophe. Economic models developed in 2025 calculate that a city-killer asteroid impact could generate damage costs exceeding $4 trillion within the first year alone. These calculations account for direct infrastructure destruction, immediate casualties, and the cascading effects that would ripple through interconnected global systems. A 150-meter asteroid striking Manhattan would instantly destroy over $500 billion worth of real estate and infrastructure within the initial blast radius. The thermal radiation would ignite fires across all 5 boroughs, adding another $200 billion in property damage. Emergency response costs would consume tens of billions more as rescue teams struggle to reach survivors trapped beneath collapsed skyscrapers and burning debris. The insurance industry has begun developing specialized coverage for asteroid impacts as actuaries recognize the growing threat to modern civilization. Lloyd's of London now offers catastrophe bonds specifically designed to cover asteroid-related losses, acknowledging that traditional disaster insurance fails to address the unique risks posed by cosmic impacts. These policies face unprecedented challenges in calculating premiums for events that occur once every few centuries, but could bankrupt entire nations when they strike. Insurance companies study historical impact rates and damage assessments to price coverage for risks that exceed the financial capacity of any single insurer. Global supply chains would face immediate disruption if even a moderate-sized asteroid struck a major industrial region. The 2025 global economy depends on just-in-time manufacturing and tightly integrated logistics networks that cannot withstand sudden interruptions. A 100-meter asteroid impact in a Shanghai industrial district would halt production of semiconductors, electronics, and manufactured goods that supply businesses worldwide. Container ships would be unable to load cargo at destroyed ports, creating shortages of essential products across every continent. The disruption would cascade through financial markets as companies lose access to critical components and raw materials. Cost-benefit analysis reveals that comprehensive planetary defense investments represent remarkable value compared to potential impact damages. The total cost of building and operating a complete asteroid detection and deflection network would require approximately $50 billion over 20 years. This investment covers space-based telescopes, kinetic impactor missions, nuclear deflection systems, and international coordination efforts. A single unmitigated city-killer impact would cause economic losses 80 times greater than this entire planetary defense budget. The return on investment becomes even more favorable when considering that effective planetary defense could prevent multiple impacts over the coming centuries. The interconnectedness of the 2025 global economy amplifies vulnerability to localized disasters beyond historical precedent. Modern cities serve as critical nodes in worldwide networks that process information, coordinate logistics, and manage financial transactions. The destruction of New York's financial district would trigger banking crises across 6 continents as trading systems collapse and credit markets freeze. Supply chain disruptions would create shortages of food, medicine, and energy in regions thousands of miles from the impact site. The psychological impact on global markets would compound physical damage as investors flee to safe assets and businesses postpone expansion plans. Space-based industries face immediate threats from smaller asteroids that could destroy satellites and disrupt services worth hundreds of billions of dollars annually. The global satellite industry generated $390 billion in revenue during 2024, providing communication, navigation, and Earth observation services essential to modern civilization. A 10-meter asteroid could destroy dozens of satellites in a single collision, creating debris fields that make entire orbital regions unusable for years. The loss of GPS navigation would disrupt transportation, agriculture, and emergency services worldwide. Communication satellite failures would isolate entire regions and prevent coordination of disaster response efforts. False alarms and impact warnings generate hidden economic costs through market volatility and unnecessary emergency preparations. The 2024 discovery of Asteroid 2024 YR4 triggered a 3% drop in global stock markets before additional observations revealed the object posed no immediate threat. Airlines canceled flights, governments activated emergency protocols, and businesses suspended operations based on preliminary impact assessments. These false alarms cost the global economy an estimated $47 billion in lost productivity and unnecessary preparations. Financial markets now react instantly to asteroid threat announcements, creating volatility that can persist for weeks after threats are resolved. Critical infrastructure vulnerability represents the most expensive aspect of potential asteroid impacts. Power grids, transportation networks, and communication systems form the backbone of modern civilization. yet they remain completely unprotected from cosmic threats. The 1989 Quebec blackout caused by a solar storm demonstrated how electromagnetic pulses can disable electrical systems across vast regions. An asteroid impact would generate similar electromagnetic effects while simultaneously destroying power plants, transmission lines, and distribution networks. Recovery costs would exceed $2 trillion as engineers rebuild electrical infrastructure from the ground up. Innovation investments in planetary defense technologies create economic opportunities that extend far beyond asteroid protection. Research and development spending on detection systems, propulsion technologies, and deflection methods generates jobs in aerospace, electronics, and materials science industries. The DART mission alone employed over 2,000 engineers and scientists while advancing technologies applicable to space exploration, satellite operations, and precision navigation. These investments foster technological advancement that strengthens economic competitiveness in multiple sectors. The economic calculations reveal a stark reality about asteroid threats and planetary defense investments. Comprehensive protection against cosmic impacts would cost less than the annual global military spending of major nations. The price of detecting and deflecting dangerous asteroids represents a fraction of the economic damage caused by a single unmitigated impact. Every dollar invested in planetary defense provides protection worth hundreds of dollars in prevented losses. Yet these financial arguments, compelling as they may be, represent only one dimension of humanity's relationship with the cosmic threats that surround us. Living in the cosmic shooting gallery, beyond the spreadsheets and economic models lies a deeper truth about our species and our place in the cosmos. Humanity occupies a unique position in cosmic history as the first species on Earth capable of understanding the asteroid threat and potentially doing something about it. For 4.5 billion years, our planet has been bombarded by space rocks of every size, from tiny meteorites that burn up harmlessly in the atmosphere to massive impactors that reshape continents and drive species to extinction. Dinosaurs faced this same cosmic shooting gallery for 165 million years without ever comprehending the danger lurking in the darkness above. Early humans witnessed meteor showers and occasional fireballs, but lacked the knowledge to connect these celestial displays with existential threats. Only in the past century have we developed the scientific understanding and technological capabilities necessary to recognize asteroid impacts as preventable disasters rather than inevitable acts of nature. The transformation of asteroid impact from science fiction curiosities to recognized existential risks reflects humanity's growing awareness of cosmic dangers. During the 1970s, asteroid impacts appeared primarily in disaster movies and speculative fiction, dismissed by most scientists as extremely unlikely events. The discovery of the KPG boundary layer in 1980 changed this perception by providing conclusive evidence that an asteroid had caused the extinction of dinosaurs. Suddenly, cosmic impacts became legitimate scientific concerns worthy of serious research, funding, and international attention. The 1994 collision of comet Shoemaker-Levy 9 with Jupiter provided a spectacular demonstration of impact dynamics, showing television audiences worldwide what happens when cosmic projectiles strike planetary surfaces. Researchers who work daily with impact probabilities and damage scenarios face unique psychological challenges that affect their personal lives and professional decisions. NASA Planetary Defense Coordinator Lindley Johnson reports that constant exposure to extinction scenarios creates a persistent sense of urgency about threats that may not materialize for decades or centuries. Scientists who calculate impact probabilities must balance scientific objectivity with the emotional weight of scenarios involving millions of casualties. Many researchers experience difficulty sleeping after particularly intense modeling sessions that simulate city-destroying impacts. The psychological burden increases during periods of heightened threat assessment when newly discovered asteroids require immediate analysis to determine impact risks. Public awareness of asteroid threats has grown dramatically following recent close calls and successful detection missions. The 2013 Chelyabinsk meteor event brought asteroid dangers into mainstream consciousness when dashboard cameras captured the dramatic atmospheric explosion that injured over 1,000 people. Social media amplified public interest as videos of the fireball and subsequent shock wave spread globally within hours. The success of NASA's DART mission in 2022 demonstrated that asteroid deflection was possible, transforming abstract scientific concepts into tangible planetary defense capabilities. Opinion polls conducted in 2025 show that 68% of adults now consider asteroid impacts a serious threat requiring government attention, compared to 23% in 2010. Society continues to debate how much resources should be allocated to defending against low-probability, high-impact events like asteroid strikes. Critics argue that asteroid defense spending diverts resources from immediate problems like poverty, disease, and climate change that affect millions of people today. Supporters counter that the catastrophic consequences of even a single asteroid impact justify significant investments in detection and deflection systems. The debate intensifies when considering that comprehensive planetary defense would cost roughly $50 billion over 20 years, equivalent to the annual military spending of medium-sized nations. Political leaders struggle to justify spending on threats that may not materialize during their lifetimes, while facing immediate pressures from constituents dealing with unemployment, healthcare costs, and educational needs. Amateur astronomers and citizen scientists play increasingly important roles in expanding our detection capabilities beyond professional observatory networks. The NEOWISE program relies on volunteers to analyze infrared images and identify potential asteroid candidates among millions of celestial objects. Amateur astronomers operating backyard telescopes have discovered dozens of near-Earth asteroids using commercially available equipment and software. The Spacewatch program at the University of Arizona trains volunteer observers to recognize asteroid signatures in telescopic images. These citizen scientists contribute thousands of hours annually to asteroid detection efforts while developing personal expertise that enhances public understanding of cosmic threats. Long-term planning for space exploration and colonization now incorporates asteroid threat assessments as fundamental design considerations. Mars colonization proposals include underground habitats specifically designed to protect settlers from asteroid impacts that could devastate surface installations. Lunar bases planned for the 2030s will be constructed in lava tubes or buried beneath regolith to provide natural protection from cosmic impacts. Space elevator concepts must account for the possibility of asteroid collisions, with cables extending from Earth's surface to orbit. These infrastructure projects require engineering solutions that remain functional for decades or centuries despite ongoing exposure to cosmic hazards. The search for dangerous asteroids has generated unexpected discoveries about the early solar system and planetary formation processes. Near-Earth asteroid surveys have identified objects with unusual compositions that preserve materials from the solar nebula 4.6 billion years ago. The asteroid Bennu, studied by the OSIRIS-Rx mission, contains water and organic compounds that provide clues about the origins of life on Earth. Asteroid orbital analysis has revealed evidence of past planetary migrations that scattered objects throughout the solar system. These discoveries advance our understanding of cosmic evolution while simultaneously identifying objects that could threaten modern civilization. Asteroid detection programs have cataloged over 34,000 near-Earth objects since systematic surveys began in 1998, yet this represents only 10% of the estimated population of potentially hazardous asteroids. The remaining 90% of dangerous objects remain completely unknown, hidden in the darkness of space until they approach close enough to Earth to reflect detectable amounts of sunlight. Statistical models suggest that city-killer asteroids strike Earth roughly once every 1,000 years, but this average provides no guidance about when the next impact will occur. We stand at an unprecedented moment in Earth's history where a single species possesses both the knowledge to understand cosmic threats and the technological capability to address them. Previous mass extinctions occurred without any life forms recognizing the approaching danger or having the ability to prevent catastrophe. Humanity has developed space-based detection systems, kinetic impactor technology, and international cooperation frameworks that could protect our planet from most asteroid threats. Yet the clock continues ticking, and the fundamental laws of physics and orbital mechanics remain unchanged. The asteroid threat demands immediate action while we still possess the capability to act. The next asteroid impact will happen. This is not a question of probability, but a mathematical certainty written in the laws of physics and orbital mechanics. City killers hit every few hundred years. Truly global extinction events strike once every tens of millions of years. We are living through the first moment in planetary history when a species can detect these cosmic threats and deploy technology to prevent them. The choices we make today about funding detection systems, developing deflection technologies, and fostering international cooperation will determine whether humanity survives the next major impact. We have the knowledge and tools. Will we use them before the next cosmic bull arrives?